Hello, everyone. This is Minglan Yu from Harvard University. Today, we are going to have another P4 workshop talk from Yanfang. Yanfang is have graduated from Wisconsin Medicine, and she's now a software engineer at Intel. And this work she's presenting is about the joint work from Wisconsin and VMware research. She's going to tell us a bit about how to achieve predictable low latency in RackScale networks. Yanfang, please go ahead.
Okay. Thank you for the introduction, Minglan. Okay, today I'm going to present our project PL2 toward predictable low latency in RackScale network. And this is work when I was a PhD student at UW Medicine and collaborate with VMware research. So these days, RackScale data centers architecture have emerged as a new building block for deploying modern enterprise cloud and edge workloads. For example, Intel, RSD, Dell EMC, VxRail are building these RackScale systems. And the first step for this aggregated resources, for example, remote memory and in-network aggregate application like NetTrain, Netcache are also built in the RackScale. Even for the traditional distributed systems, the application scheduler tries to pack their hosts into the same rack. So RackScale architecture is like this figure shows, where all the hosts connected to the one switch. These emergencies of the RackScale systems cause the network density increases. However, the switch buffer size does not increase as faster as it is. In addition, the incast ratio can be up to 5,000 to 1, as the Google's Swift paper indicated. Even in our 5-way incast experiment, we see a lot of packet job caused by the incast. Here we argue that the packet job caused by the incast cannot be avoided with the state-of-the-art congestion control. And it is even worse when the LAN rate increases and while the RTT doesn't get smaller, so RTT bytes increases. While this state-of-the-art CC always start with the LAN rate and burst with the RTT bytes. So here we did a five-way incast experiment with the receiver-driven scheme. We collect the number of the packet job every 10 milliseconds and collect the tail message latency. So here, as we can see that the packet job with the receiver-driven scheme continues happen throughout the whole experiment. And this packet job can cause the most noticeable tail latency as shown in this tail latency message figure. So the tail latency is much higher than what we proposed, our scheme called the PL2. So the essential reason that the incast caused the packet job cannot be avoided is because that we cannot predict the network traffic in a fine granularity. So PL2 seeks a new architecture for congestion control by leveraging the RackScale characteristics, that a single switch to which all the hosts are connected. So in such scenario, as all the traffic goes through a single switch, the switch can have the global knowledge of the demand and also the global coordination across all these endpoints. So we think that the recent advances of the programmable switch enable stateful processing such that the demand and the global scheduling status from all the active points can be stored. So this programmable switch offers in-transit packet processing and in-network state. And as this figure shows, users can program the switch ingress before it goes into the in-queue and the egress pipeline, and then store these states across the packets in the switch memory, which we call as register. So this architecture suggests an opportunity that we can take the switch as a centralized packet scheduler, or maybe a scheduler for the real-world upper layer application. So PL4 therefore uses a single programmable switch within a rack as an arbiter. which has a global visibility into the packet reservation requests from all the endpoints connecting to it. So one main requirement for such arbiter is that the scheduling overhead should be in the microsecond level, and the algorithm should be implemented in the switch data plane. So to design such an packet scheduler at switch data plane, it requires the switch algorithm to fit into the switch architecture, memory capacity, and also need to adapt to the restricted programming model and the memory access model. So we designed the PL2. Here I'm going to use an example to illustrate how PL2 works. So this figure now shows that the host 1 and the host 2 and the switch is timeline. And the dotted line box is the switch. When we start a switch create a scheduler of the input and output reservation for every port in terms of the time slots. At this moment, as we can see that the earliest time slots in port of the host 1, that the port connected to the host 1 is 3. And when the port acts as host 2, output the earliest time slot in the egress is 4. So now host 1 wants to send a packet burst to host 2. So host 1 first send a reservation packet to the switch to make a reservation. Then the switch reserves the earliest available time slot in H1's input port. Here T equal to 4. And H2's output port, that is 5. Then the switch notifies the host 1 of these time slots through a grant packet message. Upon receiving this grant message, the host side conservatively chooses a time slot to transmit that is available on both the relevant input and output ports. So this host 1 transmit at the max of these 2 time slots in the grant packet, which is T is equal to 5. So when the data packet goes through the switch removes the reservation for these packets. Then the data packet leaves the switch and arrives at the host 2. So this process works well when the network is highly congested. However, it experiences some overheads when the network is lightly loaded. The first part of the scheduling overhead bothers people a lot is this reservation and the grant delay, which is 2 microseconds. And compared to the end-to-end RTT that is 6 microseconds. And note that this scheduling overhead of 2 microseconds is fixed. Because PL2's reservation packet doesn't need to go through the congestion point to do the packet reservation, which can avoid the queuing delay in the control loop, and the queuing delay can be up to milliseconds because of the shared buffer model. So the other factor that impact this overhead is the request demand. Okay, if the end host sends 1 reservation packet per data packet, in other words, K is 1, then a flow with multiple data packets can add multiple 2 microseconds overhead to the overall flow finishing time. So to reduce the scheduling overhead, we first set K as 4, such that the worst case that one host sending traffic to another host case, we are able to achieve close to the line rate. Then to reduce the reservation and the grant packet delay, we therefore design an optimization that enables senders to piggyback the reservation packet with the last burst data packets. So the predictability of PL2 is that for each burst, this burst message delivered time is the waiting time plus the data transmission time. So the waiting, however, this waiting time can increase as the reservation slots increases. This is the end-to-end message latency is unbounded. So as of now, all the reservation goes to the switch, they are granted, which leads to the fact that the message latency is unbounded. if we relax these assumptions, say when some reservation goes to the switch and the switch sees that the reservation is high enough, then the reservation can be denied. So then we can bound this reservation or the waiting time at the end host such that we can bound the message latency. So the key idea to bound this end-to-end message latency is that the switch only reserve a limited time slots for packet transmission. So with this design, the max queue length is bounded by this limited time slots, say T2. As the packet number in a specific port, output port or a specific queue is always bounded by T2 numbers of the packets. Then the message latency also can be bounded by the T2 plus the reservation and grant packet reservation and grant packet delay. So here we refer this kind of message as the high priority message. The statement is that if the network doesn't have more than T2 packets demand from the high priority message, then this high priority message can be bounded with this delay plus the data transmission time. So we can distinguish whether a message is a high priority or low priority message in a bit by a bit in the reservation packet. So here is the algorithm how it works. So if the reservation packet is for the high priority message, then the switch will always grant the time slot as it requested. Then for the low priority message, if the reservation time slot is already larger than T2, then the switch will reject the reservation. If the current reservation is larger than T1, then the switch grant one time slot for the fairness purpose, because we still want the senders to move forward to have some packets to send out. And otherwise, the switch just grants the time slots as the reservation packet requested. So here we set the T1 as 64 because we need at least 64 slots to achieve the line rate. And we think 128 time slots to a bounded latency is low enough. That's why we choose T2 as 128 packets. So moving on, we implement PL2 in a customized networking stack to support PL2. And then we implement PL2 at Mellanox VMware, which is a user space TCP networking stack. For that, we can run the vanilla TCP application. Then we use P4 to implement the centralized scheduling algorithm at the Tofino switch. So we evaluate PL2 on a testbed with 6 hosts connected to one Tofino switch, and we compare PL2 against the receiver-driven scheme and TCP/cubic and UDP. Then we evaluate on the Memcached VGG16 workloads and the workloads from the HOMA paper. So first, we compare PL2 with a receiver-driven scheme with workload VGG16 using the parameter server approach. The traffic pattern is, as shown in this figure, is actually essentially is a shuffle. So here we have 4 hosts sending data as workers and 2 hosts as parameter servers, which receive gradients from all the workers. The gradient data is partitioned according to the VGG16 architecture. We repeat this process 100 times and measure the finishing time of transferring the entire gradient set at each worker at each iteration. And then we measure the finishing time. This CDF shows this finishing time of each iteration at each worker using the PL2 and the receiver-driven scheme. So here, as we can see that PL2 has lower finishing time than the receiver-based scheme. The receiver-driven approach is lower because the receiver-driven scheme only counts the queuing at the receiver. Thus, it has a well-known issue that it can experience the low utilization in the shuffle case. So in addition, to achieve 100 gradient sets exchange from each worker, PL2 takes 9.5 seconds in total, while the receiver-driven scheme takes 12 seconds. So the main takeaway is that PL2 improves this training latency for VGG16 by 30%. Moving on, here we want to demonstrate the latency sensitive RPC request in this experiment, where we measure the memcached response latency when competing with the TCP background traffic. And here we compare with the compared PL2 against the cubic on top of VMA. And in this experiment, initially we only have one memcached client send a request to the receiver with 4 kilobytes values. Then we start adding the background traffic one by one. So this background traffic is able to send with line rate. Then we measure the median and the 99th percentile latency when applying PL2 and cubic on VMA, as shown in this figure. So overall, as we can see that PL2 has lower RPC latencies than the cubic. So it's worth noting that the 99th percentile RPC latency with VMA cubic is 127 microseconds, as opposed to 56 microseconds with PL2, even with 400% of the offered loaded. So the main takeaway is that PL2 can improve the 99th percentile RPC latency up to 3x compared with the compared with cubic. However, as we can see that when the number of the hosts sending background traffic increases, the RPC latency of the PL2 also increases. This is mainly because the reservation from other flows increases, which leads to the waiting time increases, and this leads to the end-to-end message latency increases. So here we apply the bounded low latency optimization, where we prioritize this memcached traffic and measure this RPC latency as this background traffic load increases. So as we can see from this red bar, is the latency that after we apply this bounded the low latency optimization. So the end-to-end RPC latency does not increase as much as the scheme that without the bounded low latency optimization. So with this optimization, PL2 bounds the end-to-end message latency regardless of how heavy the background traffic. So in summary, PL2 is a centralized packet scheduler towards a predictable low latency network in the RackScale network. Here we develop a new algorithm by co-design the switch logic and the end host logic to achieve this. So then we also propose the solutions to reduce the packet scheduling overhead and propose an optimization to provide the bounded low latency for high priority messages or time or latency sensitive messages as application request. That's it. Thanks for listening, and I'm happy to take questions.
Hi, Yanfang. Thanks for the excellent talk. It's very interesting work. I want to start with a P4 related question. So your scheme certainly leverage a lot of features in P4. So could you share your experiences of using the programmable switches? Like what features do you find especially useful? I know you are now in Intel, and people are actively working on Tofino 2 with new queue management and signaling mechanisms. So what kind of schemes do you think might be useful in future, like scheduling and congestion control design, that may further improve your approach here if we are given a better chip.
Thanks, Minglan. So the first question is which P4 features that we used in this application?
And what limitations do you find, and what kind of feature do you think would make your life easier in designing future protocols?
I see. So I think as you probably know the fast pass. I think fast pass is it does the optimization of the matrix matching problem. Actually, this is the bipartite matching problem. And if the switch can support, or the data plane programming can support to implement such algorithm, then actually PL2 can towards on that direction. And maybe first I want to say why PL2 can first take in place. So one reason was because as you see, this reservation packet and the grant packet, they are protocol independent. So for this protocol independent P4, because the current programmable switch supported this kind of programming, then we were able to achieve the PL2. And the second part is that how can we make this P4 more expressible? Or maybe that also requires the hardware changes to support the algorithm like the fast pass proposal. And the last part would be, yes, Barefoot now have more new features in Tofino 2, maybe even the more generations of the Tofino switch that we are designing. So I think maybe JK already talked about that, and you already know that we have.
Yeah, I think just for the audience purpose, we're curious from a user perspective. When you develop protocol, like what kind of features may make future designs or your current design easier? Like what kind of features are more useful?
Yeah, one most useful feature that is very useful. Let's just talk about this congestion control perspective.
Yes.
So is that we can get the Q depths from ingress. We can get the egress Q depths from ingress. That totally avoid the queuing delay that I said before. Because in the past we do the and the congestion control, and the control loop also involves this queuing delay, and it can be. But with the PL2 and the new features of Tofino 2 all have that we get the queue depths from ingress, then immediately get back to the sender, and the sender can either stop or adjust the rate. This is most interesting feature for the congestion control.
And yes, thank you. Yeah. Any other points?
Any other points was about I think maybe JK already talked about that we can do, because of this stateful register exists, so we can take the fast, say the sender and the receiver will take a long hop, many hops to arrive at the receiver. So we can take the congestion information from the long distance receiver's switch to the sender switch. So this relies on this register, the stateful memory.
Yes, I think it's also aligned with PL2, like having the switch to communicate with the host to resolve the channel. So
yes,
it's aligned. I see.
Yes, the main difference for the PL2 is the PL2 first ask for the reservation.
Yes.
That we didn't burst out, such that it's like all the packets transmission is under the control. So we can totally avoid the incast. but might with half RTT overhead, or we can say 2 microseconds overhead.
I see. So future chips with better host and switch direct communication would either in a proactive way like PL2 or in reactive way like congestion control would always be useful. Interesting.
Yes.
Thanks.
Yeah.
So then I have a more question more related to PL2, which is I see you compare with the receiver-driven approach. So in your setup, would you expect to see, what would you expect to see for those congestion control protocol that takes one reactive and takes one round trip time to get the information? Like in your specific experiments, where do you see the benefit comparing to them?
I think the
where do you see that curve looks like?
Yeah, the main benefit was that the current congestion control, we want to take this first RTT, so they always burst with line rate, and then the incast is unpredictable.
Yeah,
that is the main. That is the.
But since you are in RackScale, right, just 2 hops, even if we rely on the one round trip time, but if we can just see the queue length ahead of time, would that still, would you expect the performance of the RTT round congestion control to have the same performance as the receiver driven curve you showed? Or do you expect them to be, where do you expect them to be? Just wondering the evaluation about the experiment, like where do you?
This experiment?
Yeah, but you're comparing with a receiver-driven baseline. What if we have better congestion control support? Would you expect the curve to still stay the same?
I think so. If that is the end-to-end loop, if it is the end-to-end, if it is controlled in the end-to-end loop, because they always need to one RTT to take effect.
Yeah.
At least one RTT, congestion control will kick in. Before this one RTT, no congestion control there.
Yes. Okay. One more question is for within your PL2, there's still a few parameters we need to set, like the number of packets we group together to reserve the channel, and the T1 and T2 threshold. Do you have recommendations for people who would like to use your protocol in their own setup? Like what would be the good way to decide these parameters?
So for that,
do they relate to the switch link speed, buffer space? Like,
here mainly the T2 is used on how many packets that you want to bound. So you want to bound for 1 megabytes, then you can set as 1 megabytes. And the end-to-end latency might be bounded by 1 megabytes transmission time. And the T1 is decided by the link speed. And we kind of found that after the BDP is around 650 packets in this setup. So we set this T1 as 64. So T1 is decided by the BDP.
Okay, thank you. So one last question. I know your design is focusing on the rack scale networks, but I think Google is seeing even more incast, but in larger scale clusters. So I wonder, do you see a direction towards cluster scale scheduling? Like what would be potential ways to get this approach scale?
Thank you, Minglan. And we have thinking this problem for a long time. And so one way to support the cluster-wide or multi-hop more large-scale cluster was that we still sending the reservation packet until to the last hop connected to the receiver. And at that, I think this is like INT, but the INT is not get from the switch, is from our reservation. Mm-hmm. So as you see, we always have this input port status and output status. So each time, whenever a reservation packet goes through one switch, we can get the max of both two. Mm-hmm. So for that, then we came back. But for that, the scheduling overhead would be half RTT or half RTT minus one hop. Mm-hmm. Again, this is base RTT, not taking the queuing delay. Mm-hmm. That's it.
Okay, do you expect the longer RTT because it would cause any problem for approach because it's baseline, it still will give us enough benefit?
Yes. Also, because this, as you see, there's a 2 microseconds or 10 microseconds. When we actually apply to the application is also has its own overhead. Mm-hmm. So 2 microseconds or 10 microseconds, sometimes it's not a big issue.
Yeah, it depends on the application. I think a lot of application could benefit from, would not care about this delay, but there would also be cases that these 2 microseconds may be relevant. Okay, thank you very much for sharing your work and your experience with P4. Yeah.
Thank you. Thank you.